All right, here we are. So we're going to pick up where we left off yesterday with chapter 10. We're not done with it yet. We still have a ways to go. So let me go get that open. And so let's see. All right, so you recall from yesterday that hypothesis testing is a 6-step procedure. And again, it looks a lot more complicated than it really is. All of this is really just the setup to how this process works. So we discussed the null and alternative hypotheses. And you might recall the null hypothesis is what we think is true, or we assume is true, and we'll continue to do so unless we find strong contradictory evidence. If we do, what we will do then is reject the null hypothesis in favor of what we will call the alternative hypothesis. So there's always got to be two hypotheses for any situation, the one that we assume is true, and then one we will accept in its place if we can prove that the null hypothesis is false. So the null is always written as, in the case of the mean is equal to some specific constant, which we'll specify. So mu with a little subscript of 0 means a constant. For example, if we think that the mean age of the students at purchase is 20 years old, then we will use 20 right here. And we will continue to believe that until we find evidence that it's different than 20. Now, the alternative hypothesis can be set up in 3 alternative different ways, and we called them the two-tailed, left-tailed, and right-tailed tests. But what that specifically refers to is this. In the case of the two-tailed test, the alternative, which by the way is designated H1 instead of H0, the 0 means the null, 1 means the alternative. If we reject the null hypothesis, then only one of 3 things can happen. Either the mean is not equal to the value that we specified, in which case we're basically saying that it could be below or it could be above. We don't really care in this case. We just want to know, yes or no, is the mean equal to a specific value or not? But if we're looking for evidence that the mean is greater than some value, we use a right-tailed test. Like, here's a good example. What if the US government wants to find out if the average age of all Americans is higher than it was 20 years ago? We're looking for strong evidence that the mean has gone up since 20 years ago, and so we would conduct that as a right-tailed test. Then for the left-tailed test, we're looking for evidence that the mean is below a specific value. So let's say that we're looking for evidence that the mean price of gas has fallen in the last 10 years. Then you would set that up as a left-tailed test, because you're looking for evidence that the mean is less than some specific constant. So this choice depends on what you're trying to prove or disprove. All right, so every situation is different. So, but in the problems that you'll be given, it should be pretty clear from the way it's written whether or not you're supposed to use a two-tailed test, a right-tailed test, or a left-tailed test. So when we get to our first example, you'll see it's a pretty straightforward decision. Now, the third component of this process is the level of significance, which actually we've seen before in chapter 9. You might recall that when we were trying to construct a 95% confidence interval, we had this term alpha, which was equal to 5%. That alpha is known as the level of significance. All right, so now in the confidence interval chapter, it's the 95% part that we're really more interested in. Here, the level of significance has a special role to play. And what it refers to is a specific type of error that we could make when we test our hypothesis. So let me jump ahead here and remind you that this level of significance, or alpha, refers to the probability of committing what we will call a type 1 error. So I put together a little chart for you so you can remember what that actually means. And so in this chart, you'll see that there's only 4 outcomes that can happen with a hypothesis test. There's 2 ways we can make the correct decision, and there's 2 ways that we can make a mistake. So if the null is true, but we reject it anyway, we are said to have committed a type 1 error. If the null is true and we don't reject it, then that was the correct decision, of course. And again, down here, if the null was false and we failed to reject it, that means we did the right thing. But if the null was false and we did not reject it, then that means it's a type 2 error. So something like this, you really just have to memorize it or have a chart in front of you while you're taking the test. There's nothing in that name that suggests what it means. In other words, I don't know how these names came about. It sounds like they were completely arbitrarily chosen, but we're stuck with them. So just remember, type 1, we reject when we shouldn't have. Type 2, we fail to reject when we should have. And in the context of the jury trial, a type 1 error means we've convicted an innocent person, and the type 2 error means we've acquitted a guilty person. In other words, we let them go. Maybe there wasn't quite enough evidence to prove that they were guilty. So our justice system is set up to make sure that it's very difficult to convict an innocent person, not as difficult to convict a guilty, to fail to convict a guilty person. In other words, the feeling is that the type 1 error in this case is much worse than the type 2 error. And in medicine, we often see this, we try to keep the type 1 error as low as possible, because that might mean that we accept a drug that we shouldn't have, or that type of thing. All right, and by the way, we also use the letter beta to represent the probability of a type 2 error. We're not going to get more deeply into that, except just to mention the fact that while the type 1 error has the letter alpha, the type 2 error is referred to as beta. And you also sometimes hear this, this word power, which just simply means 1 minus beta, or you can think of this as the likelihood of rejecting the null when it actually is false. Ideally, the power should be as high as possible. Now, here's an interesting twist too. The alpha and the beta, what happens is the lower is the alpha, the higher is the beta. So the way it's set up, and unfortunately, they don't add up to 1. That would have been very convenient. Okay, but let me just slip this in here, just in case it's not clear. For a given set of data, the lower is alpha. In other words, the probability of a type 1 error. Let me see if I can find that symbol. Ah, yes, there we are. The greater will be beta. Okay. And vice versa. The only way to simultaneously lower both of these probabilities is to use a larger sample size. Okay, but with this amount of data that we have, whatever it is, there's always a direct trade-off between alpha and beta. But if we want to reduce both of them, the only way to do that is to have a bigger sample size. Okay, because remember what's happening here. We're trying to draw conclusions from a population. The bigger the sample, the closer we are to having the entire population. And therefore, the likelihood of making mistakes is much lower. All right, well, anyway, now in the problems, by the way, that you'll be given, it will tell you which level of significance to use. You don't have to figure that out yourself. They have to tell you in the problem what to do about alpha. And we're not going to cover beta from this point on. In other words, calculating beta is a very messy, complex process. So we're not going to do that here. You'd have to save that for a more advanced class. So, you know, it's one of those things, like there's a lot of more discussion we could have about all of these topics. And you might, if you do find yourself in a more advanced class, you'll see some of this stuff, but not here. So all you have to remember here is that what alpha represents, what beta represents, and other than that, the actual value of alpha will be given to you in the problem set. All right, now, and here's another hint here, another side note. In most of the cases that we'll run into in finance or economics or other business applications, 5% is typically the level that you'll choose for your sigma. There's no particular theoretical reason for that. It just seems to work very, very, very well for these types of applications. In other disciplines like medicine, you might see a much smaller number here, because then the risks are greater, of course. And so you want to be extra, extra careful to avoid type 1 errors. Okay, now this is where we basically left off. Now, how do we decide whether or not we have enough evidence to reject the null hypothesis? There has to be some way of doing this, and we do. We create what's called a test statistic. And so what's actually happening here is that you're trying to figure out how close your sample mean is to, or how far away it is from the mean of the entire population. So let me just give you a quick example of this. Suppose that our null hypothesis is that the average age of all Americans is 29. We draw a sample, and the sample mean, 27. Now, here's the problem. Is this sufficient? Is this strong enough evidence to suggest that we should reject the null hypothesis? Well, it's hard to tell because we're comparing 27 with 29. Is that big enough? Is it not? Who knows? So what we do instead is the test statistic is used to convert our results into the number of standard deviations that the sample mean is away from the population mean. So we don't want to think in terms of years. Like here, we're thinking in terms of years, but it's hard to judge whether or not 27 is enough to suggest that this null is wrong, because we know that every sample mean is different. What we do, our strategy is to convert this into standard deviations. Okay, once we have standard deviations, it's much easier to judge how likely it is that our null is true. So let's just say, and I'm going to just make these numbers up right now, that we have two graphs, the original data where the mean is 29, or the hypothesized value is 29. Our sample mean is 27. If I convert these into standard normal form, suppose that 27 is only one standard deviation below the mean. Okay. Now, what's interesting about this is that this tail area is not that small, about 15.87% of the time we should be at or below one standard deviation below the mean. So it might seem like there's a pretty decent chance that the null hypothesis is true in spite of the fact that our sample mean is 27. So what we're going to do is create this test statistic, which converts our results into standard deviations, and then we'll compare them to a benchmark, which is known as a critical value, before we make our decision. All right, so let's go through the calculations and then we'll tie it all together and see what this actually means. Okay, so if the population standard deviation is unknown, just like in chapter 9, we're going to use the sample standard deviation and we're going to use the t-distribution. Okay, so remember how this works. Sigma is unknown. Use t. Sigma is known. Use z, the standard normal. So if you look at this value, the purpose of this calculation, would you recognize all these terms? This is the hypothesized population mean. You can tell by that little zero there. X bar is clearly the sample mean. Now, this is our sample standard deviation, of course. This n is our sample size. And you might also recall from the last chapter, this term is called the standard error of X bar. This is what makes it possible to convert these values into standard units or standard deviations. So that instead of knowing the actual values like 27 and 29, we have standard deviations. Okay, now if we do know the population standard deviation, the formula will be very similar, as you'll see, except that we're using the known population standard deviation, and this will be based on the standard normal distribution. Okay, so here it is. Oh yeah, it's almost identical, isn't it? Except that this is now the population standard deviation. And we're using the standard normal distribution. Either way, we're converting X bar in its original units into a given number of standard deviations away from the mean. Okay. So then we have to compare this result with something to make a decision. And that's something, and we've seen this term before, these are called critical values. You might recognize these from the previous chapter. For example, when we had a confidence interval involving the population, where we knew the population standard deviation, and when we didn't, it was down here. This value was referred to as a critical, it's called a z-score, but it's in this particular context, it's more often called a critical value. And the same thing is true down here. This is called a t-score or a critical value. So you've already calculated these. But in this chapter, though, there's more than one way of doing this. And that will ultimately depend on the alternative hypothesis that you've chosen. So there's a chart here somewhere. Okay, let me show you this chart. Okay, so when we're dealing with the standard normal distribution, there's three potential critical values that we could run into. For a two-tailed test, we have plus or minus z alpha over 2, just like a confidence interval. In fact, I just want to mention this in passing here. A confidence interval is equivalent to a two-tailed hypothesis test. They're basically the same thing. They're just different ways of getting at the same information. So therefore, what just happened? I'm very annoyed right now because I didn't know I could even do this. It seems to have deleted my undo command. Oh, for Christ's sake. It really annoys me to know when you can accidentally do so many damaging things with the slightest stroke of your pen or your mouse. I need that thing. All right, I'll have to do this all over again. There it is. It's just unbelievable. All right, let's try that again. A confidence, and now it's making it purple. Okay, that's nice. Thank you. A confidence interval All right, let me try one more thing here. Okay, it just plain ignored me. I told it to put undo on here and it just ignored me. Isn't that nice? Oh, thank you for actually obeying me. Isn't that nice? All right, so a confidence interval, unreal, is equivalent to a two-tailed hypothesis test. And so you can see they're the same. But if you have a right or a left-tailed test, what happens, if you notice, it's either a positive or negative value, and you only have alpha rather than alpha over 2. So we can illustrate this with some graphs. In fact, I've done exactly that for you. Let's take a look at how this works. Suppose that we chose alpha as 0.05, as we so often do. And so we're running a hypothesis test at a 5% level of significance, but it's a right-tailed test. So according to this chart, my critical value is Z alpha. So what does that mean? It means that I'm looking for a Z-score or critical value where 5% of the distribution is above that point and the rest is below. So I went to the charts, or you can use INV norm on your calculator to find that the equivalent Z-score is 1.645. It's actually halfway between 1.64 and 1.65. So we'll call that 1.645. And so this is what we end up with. So that 1.645 is what we mean by Z alpha. And so the 1.645 is our critical value. And that's the benchmark that we will use to determine if we should reject the null hypothesis. What if we have a left-tailed test, though? Then we just use the negative of the right-tailed test. Okay, it's the same value for the Z-score or critical value. It's just negative. All right, let me jump down here a little bit. You can see, due to the symmetry of the curve, that would be negative Z alpha over 2, Z alpha. And then if it's a two-tailed test, this is what we're more familiar with. You have plus or minus Z alpha over 2, which means half of that 5% is in either tail of the distribution. So that picture, and we looked that up in the calculator, and that turns out to be 196, which you've seen in chapter 9 many times. So here we have two critical values, positive Z alpha over 2, negative Z alpha over 2. So what are we doing with this information? That's the interesting part. The way it works is, I'll put this in here as a separate slide. If you notice, each time I've shaded the tail areas. So the logic behind what we're doing here is this. If the test statistic is large enough, or I should say extreme enough, because it could be negative as well, to fall in the shaded region, tail area, then we reject the null hypothesis. Otherwise, we do not. Okay, so in other words, if you look back at this last graph, in fact, I probably can fit it on here. Let's use the two-tailed case as an example. This shaded region is often referred to as the rejection region because if the test statistic is in here, that means we have to reject the null. Okay, so if the test statistic, in this case, if the test statistic is greater than 196 or less than negative 1.96, that means we reject the null. And if we reject the null, of course, we accept the alternative. Okay, so that's why they're there. They're, like I said, they're benchmarks that we can use to make a decision. Is the test statistic extreme enough to cause us to reject the null hypothesis? So that's what these are for. So you actually calculate these together because we need them both to make a decision. Now, just as a quick review, remember way back here, we had that case of the population mean age. And in this case, we're only one standard deviation below the mean. So if our critical value is negative 196, that means we're not going to reject the null. Okay, so let me just fill this in here. So that means our critical values would have been plus and minus 196. If our test statistic put us here, that means we would not have rejected the null because it's not in either tail. All right. Now, if we have the case with where we don't know the population standard deviation, we have to have a new set of critical values taken from the t-distribution, but they're set up in exactly the same way. Okay, so when sigma is unknown, instead of using the standard normal, you notice we're just doing the same thing with the t-distribution. The only extra detail here is we're always going to have n-1 degrees of freedom in this chapter. Other than that, the logic is exactly the same. These are all taken from the t-distribution. And in fact, I have some nice graphs to illustrate this. So imagine that we're using the 5% level of significance, as we so often do. And we have a sample size of 20, which implies 19 degrees of freedom. So you can look up the critical values in a table, or you can use the INV-T function in your calculator, as we've seen. And we get a value of 1.729, which, if you recall, with the standard normal, it was 1.645. So the T critical values are always larger than the standard normal ones. So if we had a right tail test, the critical value is 1.729 because now 5% is in the right tail. If we have a left tail test, we just move to the other side. Because of the symmetry of the distribution, we're going to have negative 1.729 in the left tail. And I'm sure you can guess what's coming next. We have to have the two-tailed case. So we go back to the table, and for two-tailed, where only 2.5% is in either tail, the critical value becomes 2.093. And so this is what we end up with. All right. And then finally, the decision rule, we've already kind of discussed that. Basically, in a nutshell, if the test statistic is in the rejection region, and I'd like to summarize that again here somewhere. Well, I think we already get it. The right tail test means that if the test statistic is greater than the critical value, for example, using the example we had, let's say this is the standard normal. This is my rejection region. In the left tail case, and again, this is for the standard normal case. And then, of course, with the two-tail test, we're splitting it up between two tails. So we'll have two different halves of the rejection region, you could say. And we'll split it up like this. So you can think of the rejection region here as having two halves. Either one will cause us to reject the null. All right, so finally, with all that theory behind us, we can do some examples. Once we start doing the examples, it'll be so much more straightforward. It must seem like a nightmare right now, but once we've done it a couple of times, you'll realize, no, this isn't that bad. Okay, so remember earlier we talked about this government that wanted to know if the mean income of its households is greater than $25,000 per year. Now, the fact that they want to know if it's greater than, already that's a hint that this is a right-tailed test. Right tail, because it says greater than. We're looking for evidence that the mean is greater than 25,000, but it has to be strong evidence. So we draw a sample of 100 households, and we calculate the sample mean. And in this case, it turns out that we are going to assume, or that we know, the population standard deviation. Okay, so we know that n is 100, x bar is 27,200, and s is 8,400. And that tells me immediately, use, oh wait, sorry, I wrote the wrong one, sorry. Population, it's sigma, that's right. Use the standard normal, or Z distribution. Okay, so, oh, you know, I forgot to do one thing here, hold on. All right, so first things first. So, well, we already have the null and the alternative. And we will reject the null if we have sufficient evidence, which means that the test statistic exceeds the critical value. Now, the level of significance, let's just say that it's 5%. All right, and of course, remember, that's the probability of a type 1 error. And this is a common choice with business applications, although we can certainly use 1 or 10 if we want to. Now, we did mention that we know the population standard deviation, so this is our test statistic. There's two choices here, remember, T or Z. Anyway, so we'll use the data that we have to come up with our test statistic. And now remember, this mu0 is the hypothesized value of mu. The others we recognize. All right, just don't forget about that one. And so we'll plug in those numbers. Okay, so remember, the sample mean was 27,200. The hypothesized mean was 25,000. The population standard deviation is 8,400. The sample size is 100. And when all the dust settles, you've got a test statistic of 2.62. Now, 2.62 is pretty far above the mean. Already, we're kind of suspicious that we may be rejecting this null hypothesis, but let's prove it. We still have to calculate the appropriate critical value so that we know what the benchmark is that we can compare this with. Now, we did this earlier with a 5% level of significance and the standard normal distribution. We wind up with a critical value of 1.645. Only 1.645. It's not that high. So we can come up with that, of course, from the tables or INV norm. Okay. So in other words, what this is telling us is that if our test statistic exceeds 1.645, we're going to reject the null hypothesis. Well, we've already seen that that's indeed what happened. Critical value here, the shaded region is the rejection region. The test statistic is this 2.62. And that means that the mean, the sample mean, is so far above the population or the hypothesized mean that we must reject the null. All right, so the test statistic is indeed in the rejection region. And that means we reject the null. Okay, so the decision then is to reject the null. So let's see. No. So in other words, if you go back and revisit the null hypothesis, the sample mean was quite a bit higher than 25,000. What was it, 27,200? Yes. Now, like I said, it's hard to tell from looking at these two numbers if we should reject. Oh, wait a minute. What did I do? Hold on. This is still, no, X bar was 27,200. So the long and short of it is that 27,200 is far enough above 25,000 to be inconsistent with the null hypothesis. So if you drew this distribution with the original data, you'd have your 25,000 here and 27,200 is way up here somewhere. If you convert this to the standard normal form, you have 0 and 2.262. But since the critical value is here, you're definitely in that rejection region, and therefore you reject the null. All right, and so now whatever they were planning on doing, let's say the government, if that turned out to be the case, they were planning on, I don't know, raising taxes or something. Now they can go ahead and do it because they have evidence that the mean is actually greater than 25,000. All right, now here's another example. It's the same government, all right, now they're studying the farmers in their country. They're looking at the crop yields of the wheat farmers, and they want to know if the mean yield is equal to 10,000 bushels per year. Now, if you notice this time, they didn't say we want to know if the mean is greater than 10,000 or less than 10,000. That tells me that this is a two-tailed test. So sometimes you have to interpret it very carefully. If it doesn't specifically say, we need to know if it's above 10,000 or below 10,000. We just want to know if it's equal to 10,000. That means the alternative will be unequal to. So in other words, the null will be, the mean is 10,000. The alternative will be that it is not. So again, that part depends on the way the question is worded. So I try to always make these questions as clear as possible, but you may have to interpret a little bit. You want to make sure you know which one you're dealing with, left, right, or two-tailed. Otherwise, you cannot get the right answer. All right, so this is different. Now, this is a small sample case, and we don't know the population standard deviation. So N is 8. The sample mean is 8,900. And the sample standard deviation is 420. So sigma is unknown, which tells me right off the bat, use the t distribution. All right, so now we go ahead, we write out, we go through all the steps, we write out the null and the alternative, which we already know, but here they are. And once again, why don't we assume that the level of significance is 5%. So already we know the first 3 steps of our 6-step process. How do you like that? So already we got half of the work done. So what's next is the test statistic. And since we saw already that we don't know the population standard deviation, that means we automatically use the t distribution. And so here's our test statistic. Oh yeah, that's right. This is the one we use when we don't know the population standard deviation. But it's the same calculations. All right, if you notice, it's x bar minus hypothesized mu. Here in the denominator, we have the standard deviation over the square root of the sample size. So the next step is to simply plug in the numbers and calculate your test statistic. Now, in this case, the test statistic is quite extreme, as you'll see. We're way below the mean in this case. Okay, wow, negative 7.41. That's pretty far into the left tail. So it looks like we're probably going to reject the null, but first let's prove it by calculating the appropriate critical values. Remember, there's 2 of them, because this is a two-tailed test. We also know that it's 5% level of significance and the sample size is 8. So on the slides here, I put in the information for INVT. Just be aware that you've got 0.025 in either, oh, there it is, in either tail. The INVT function, though, what you can do is you can put 0.975 because that's everything below this. And 7 degrees of freedom because n is 8. And you'll end up with the correct critical value, which is plus and minus 2.36. Those are the boundaries of our rejection region. Okay. Anything, if the test statistic is greater than positive 2.36 or less than negative 2.36, we will reject the null. Okay, so let's do it. Let's draw the graph. And you can see I've drawn out the rejection region. Look at that test statistic. It's way, way out there in that left tail. So this is my test statistic, and you can see it's clearly in the left tail of that rejection region. So the only conclusion we can draw from this is that we will reject the null hypothesis. Okay, so let's go to the next slide. I just have to write one thing down here. I just noticed there's a typo in my slide. I want to fix it. All right. All right, so let's keep going. Okay, now this is what we're about to see is an alternative way of going about this. Now, this gives us equivalent results to what we just did, but the reason why we're doing this here is because when you use your calculators to test hypotheses, they use a slightly different approach than what we do here. They give us a number called a p-value, which we can use to easily determine if we should accept or reject the null hypothesis. So we need to be familiar with what p-value actually means, because the calculator is going to give that to us instead of what we did here. Specifically, the calculator will, at least the Texas Instruments ones, will give you the test statistic, but not the critical values. You can still look those up, but it's easier to simply go with the p-value. So what exactly is the p-value? This, formally, it represents the probability that the test statistic is at least as extreme as the observed value when the null is true. All right, now I know that's very abstract and very bizarre, so let me show you what that actually means. Why don't we revisit that first case we had when we were testing whether or not the mean income in that country was $25,000. And you remember the critical value was 1.645. And the test statistic was 2.62. Now, we use that result to determine that we should reject the null because the test statistic is in that region. The p-value, and I'm going to calculate this real fast in my calculator. Hold on 1 second. It's being stubborn with me. All right, here we go. So what I'm actually doing, I'll show you in a second. .0044. This region here has an area of 0.0044. This is the p-value of our test. Essentially, what this represents is the probability that z is greater than or equal to, oh, wait a minute. I don't, now that I think about it, I think it wasn't 2.62. It was 2.262. All right, I have to fix that, sorry. Let's get that fixed. Yeah, that's gonna be off a little. It was 2.262. That's better. All right, so I'm gonna recalculate that since I goofed it up. All right, that's better. It's 0.0118. So basically, you can think of it as the probability of getting that test statistic or something even larger when the null is true. But it really just means the probability, that whole area, which is more extreme than the test statistic. So what are we supposed to do with this information? Well, first things first, a low p-value indicates that it is unlikely that the null is true. Now, if you notice, the entire shaded region in my diagram is 5%, of which only 0.0118 is the p-value. So that is the logic behind what I'm about to say. If the p-value is less than alpha, and by the way, this whole region does have an area of alpha, then we reject the null. Of course, otherwise, of course, do not reject the null. So I'm going to, in a few minutes, I'm going to show you how to test hypotheses with your calculator. And like I said, you're going to put in all the same information, but it's not going to tell you the critical values. It's going to tell you the p-value. So I guess the calculator manufacturer feels that this is quicker and easier than using the traditional approach of comparing the test statistic with critical values. And they're probably right, because all you have to do is look at the p-value and say, well, is it below alpha or is it not? That's all you need to know. So at this point in time, virtually all calculators and software programs use this approach to test hypotheses. In fact, one of the books that I was looking at actually described what we were doing before as outdated. I couldn't believe it when I saw that. Outdated. But it's still the same thing. It's basically the same process. You're just coming at it from a different direction. You know what I mean? It's like, It's like saying that, well, driving is outdated. Well, I guess it is, but I mean, they're still both useful techniques. All right, so this is it in a nutshell. Oops, it looks like I messed up this one too, didn't I? Let's see, I have to make a note of this. All right, so I need to make a little repair here. That's very frustrating. All right, so I've somehow I made the same mistake twice. I guess I wasn't paying attention. 2.262. All right, now it's fine. Okay. All right. Oh boy, God, even this is wrong. All right. Now for this other one, with the the bushels of wheat. In this case, the t-value is so tiny. Look at that. The test statistic is minus 7.41. The p-value is really tiny, but this is an important detail. When you're dealing with the p-value, if you have a two-tailed test, you're including the area in both tails. So each tail has an area of 0.00074, which we can look up on the t-tables or in your calculator, but here you add them together. So the actual p-value in this case is the sum of the two tail areas. It's this number right here. So you have to pay close attention to that. That's not the case with the right or the left tail test. But with the two tail test, you have to add up both tail areas to come up with the correct p-value. All right, that's the only other thing you needed to know. So now, what we're going to do is learn how to do this with the calculators, okay? So let's go back and revisit the case of the household income. So I wrote down again all the data that we had. So on your calculator, you're going to go to that menu, Stat Tests. And you're going to ask for Z-test, which is actually number 1 on the list. How do you like that? Now, when you get there, you have to make sure you're in the stats menu. There's 2 menus, data and stats. You don't use data unless you actually have the original data. Here, all we have is the summary measures. If you have the original data, you can use the data menu instead. But here we don't. So what happens is, the way it's set up is the first thing they ask you is for the hypothesized mean, which is 25,000. the population standard deviation, which is 8,400, the sample mean, which is 27,200, the sample size is 10. Now, down here at the bottom, there's a menu where they offer you the chance to choose between a two-tail test, a left-tail test, and a right-tail test. Now, you have to be careful with this one. You go over to the one you want with the arrow key, but when you get there, hit the enter button to make sure it knows which one you want. Okay, without enter, it may not understand what you're doing. Okay, so use the arrow key. I'll add that right here. To select the alternative hypothesis. But when you get there, make sure you hit that enter button. Now, when you hit the calculate button, it's going to come back with a bunch of details. I've only written 2 of them down. Oh, now wait a minute. Oh boy, you know what? I'm wondering if maybe the mistake that I made was not down here, but up here. Oh God, that would be terrible. No, you know what? Oh, maybe I had it right the first. I thought it was 2.262 for some reason. Oh boy, it's possible. Oh boy, what's going on here? Hold on. Let me double check this one last time. Is it 262 or 2.262? Well, there it is. I don't know what's wrong with me today. It was 262 in the first place, so I never had a mistake in there. It was 262. All right, now I have to unfix all this. Somewhere along the way, I got this thing confused. All right, so this is 2.62. That's right, I'm gonna fix it right now. That was only for the first example. It doesn't affect this one. So, all right, well, I guess I was right the first time. There's nothing to change, so let me fix it back. Okay, I think we're done. Yeah, sorry about all of that. I don't know why. For some reason, somewhere along the way, I made one little mistake, and I guess it translates. Now it is set up correctly. We're all good. Okay, good. So yeah, that's how I know that it was right the first time, because the calculator is saying that it's 262. It's doing everything for you. You don't have to do any work. You don't have to calculate the test statistic. You don't have to calculate the p-value. You just type in all those numbers, 25,000 for the mean. Standard deviation is 8,400. The sample mean is 27,200. The sample size is 100, and it's a right-tailed test. And when you run, yeah, it's 2.62 and 0.0044. Huh. All right. And then, of course, since the significance was 0.05, that means P is below that, and we reject the null. And with the crop yields, this time we pick, because we don't know the population standard deviation, we're going to use t-test, which is number 2 in the list. And again, you go through and type in all the numbers, but make sure this time you choose the two-tailed test. All right, so it's stat tests. And so we have 10,000, 8,900, 420, 8, and two-tailed. Now, this time we ran into an interesting situation. The p-value is so small, it actually says in your window 1.484, we don't need the rest of it. Way at the end, if you notice, it says E minus 4. This means 1.484 times 10 to the minus fourth power, which means 0.0001484, which is what it says here. And again, because P is well below alpha, we reject the null and accept the alternative. All right, and by the way, tomorrow, we are getting late here. We've got one more topic. Tomorrow, we're just going to practice. Just go through and just have examples and practice. Because this, once you've done enough of them, it'll become second nature. It looks like I said, very complicated. But once you've done enough of these, you'll be an expert in no time. Okay. So now what is left to do is test hypotheses about the population proportion. So we're going to use the letter pi, as we've been doing all along, to represent the population proportion. And don't forget that lowercase p, we're going to use to represent the sample proportion. And this is the hypothesized proportion, of course. All right. Now, the alternatives, as always, there's 3 possibilities to choose from: left, right, and two-tailed. But they're, of course, going to be written a little differently because now we're dealing with the population proportion. So, but this should come as no surprise to you. This is my right-tailed test. This is my left-tailed test. And this is my two-tailed test. You notice how it's the same setup. Greater than is right-tailed, less than is left-tailed, and unequal to is two-tailed. Now, the test statistic, of course, is different now because we're dealing with the proportions rather than means. I've actually written it in 2 stages. Let me do this real fast, just so you can see everything side by side. You've got, now the logic behind the test statistic is exactly the same as the others that we've seen. You've got the sample proportion. This is a hypothesized proportion. This is the standard error of P. So the formula is a little messy, so I wrote it separately, but this is how we did all of the others as well. We've got the sample version, the hypothesized version, divided by the standard error. That's our test statistic for the proportions. All right, let's do an example. And the 6 steps are the same. Everything's the same. It's just really the only thing that's different is the test statistic when you come right down to it. So suppose the US government believes that 15% of the population is retired, but they are testing to see if it's higher because if it is, they might raise the age at which Social Security may be collected. So here's the sample. They pick a random sample of 100 people, and they find that out of these 100, 17 are retired. So you might recall the notation we used yesterday. X is 17, N is 100, which means the sample proportion, which is X over N, is 0.17. Now, remember too, they're looking for evidence that the proportion of retirees is higher than 15%. Okay, now the current statistics show 15%, but they're concerned that the actual number may have risen so that it's actually higher than 15%. So this is clearly a right-tail test. So here's the null hypothesis, which means that the proportion equals 0.15 as we continue to believe until we find evidence that it's not. And then it's a right-tail test because we're looking for evidence that the proportion rather may have risen above 15%. So therefore it's a right-tail test. They don't care if it's below. That's not a problem, all right? If it's less than 15%, then the Social Security system is sound, or well, it's less likely to fall apart. So let's choose alpha to be, as usual, 5%. And then let's construct our test statistic. Okay. So this is what we know so far, which we've already seen. Oh, sorry. The sample size is 100. The hypothesized proportion is 0.15. The number of people in the sample who are retired is 17. So the sample proportion is 17. Now, the standard error, which we can calculate separately because it's kind of messy, is, okay, 0.15 times 1 minus 0.15 over 100. We take the square root of that. The standard error is about 0.0357. So with all that in place, now we can easily calculate our test statistic. Now, I mentioned this yesterday. When you're dealing with proportions, you never use the t distribution. This is guaranteed to be based on the standard normal. And so when you go to your calculator to look for the right function, you'll see that there is no t proportion test. All right, so having said all that, the actual test statistic is sample proportion minus hypothesized proportion over standard error. It's about 0.56. Now, that's not a very large number. And we've already seen that when we have a right-tail test with alpha of 0.05, Z alpha is 1.645. But our test statistic is way in here. It's really not even close to the rejection region. So what that means then is that we're not going to be able to reject this null hypothesis. All right, the test statistic is much too small to land in the rejection region. And therefore, our conclusion will be, do not reject the null. Now, what we can also do is calculate the p-value. Now, I'm going to use the blue to do this again. So I've already gone ahead and done this. The p-value is 0.2877. The p-value is the probability that z exceeds 0.56. And so the p-value is well above alpha. So based on that logic, we also do not reject the null. So we've proven in two separate ways that we do not want to reject the null. It's really not even close. And what that means is that the proportion of retirees has not risen above 15%. All right, so why don't I show you where to find this in the calculator. All right. By the way, at the end of this chapter, you'll see there's some technical requirements that are needed for this to work properly, but we won't go over that right now. I just want to show you how to do this on the calculator. So it's to calculate or test hypotheses about the population proportion. Go to Stat Tests. And this time we're looking for number 5, one prop Z test. And when you get there, it's going to ask you for a few things. For example, P0. Now, the calculator sometimes uses slightly different notation than we do. It doesn't use pi like our book does. The P here actually means hypothesized proportion. Which in our case is 0.15. And then it asks for X, which unbelievable. Maybe you could stop doing that. Okay, it was 17, N was 100. And then, as always, you have the option of 3 different test statistics. Alternative hypotheses, which in this case is listed as greater than P0, which you will choose. And make sure you hit the enter button. And when you do all of that, you will of course get your test statistic, which we don't really need because we're looking at the p-value. All right, here we go. So it starts out with, it tells you what the hypothesis is. Z is 0.56, which we already knew, and P. Now here you have to be careful with all the P's floating around. This P is the P value, and that's 0.2877 as we've already figured out. So that means, of course, since the P value is greater than alpha, we do not reject the null. So you can see it's pretty straightforward. Okay, so I think that's all we need to do here. So the chapter is basically done. What I would like to do tomorrow is focus on examples. All right, just do a bunch of examples from start to finish, just to get our hands on the calculator and remind ourselves what this is all about. But like I said, once you've done enough of these, as complex as it sounds, it really will make sense by the time you've done enough of them. All right, so we'll stop right here. And I'll see you tomorrow. Tomorrow, of course, is our last class. Try to have your midterms in by tomorrow, and the rest of your problem sets hopefully are done. So then, as I discussed yesterday, the final exam will be replaced with just chapter 8, 9, and 10 problem sets. So when we're done tomorrow, the only thing you still will have to do is the chapter 9 and 10 problem sets. That's it. And then you're completely done with the course. And then you can go off and do something else with your newfound knowledge of statistics. All right, hopefully you'll see it again in your courses in the fall. It'll come in handy eventually, don't worry about that. So, all right, so I guess I'll just see you all tomorrow then at 9 o'clock, and we'll just wrap it up with a bunch of examples and any last minute questions. Okay, so I'll see you tomorrow.